Hello guys, welcome to this class, Introduction to Analytical Chemistry. What is analytical chemistry? We can define it as analytical is the science of obtaining, processing, and communicating information about the composition and structure of matter. In other words, it is the art and science of determining what matter is and how much of it exists. So we can look at this in two different perspectives. That is qualitative, where you just provide information about the identity of an atomic, molecular, or biomolecular species. Also quantitative, provide numerical information as to the relative amounts of species. So the roles of analytical chemistry, they adapt proven methodologies to new materials or to answer new questions about their compositions. So they are the people who come up with the new methods of analyzing chemical matter, and they go deep into knowing what is in those materials. Analytical chemists work to improve existing techniques to meet the demands for faster, cheaper, more sensitive chemical measurements. And this we'll talk about more when we start dwelling on analytical techniques. So analytical chemists research to completely new types of measurements, and they are at the forefront of utilization of major discoveries in fields as diverse as photonics and implantable microchip sensors. So because they are the people who understand it better, they will be on the lead to try to understand it and even to use it. So analytical chemists majorly work in medicine, in the industry, environmental, our environment, food and agriculture, the forensics, archaeology, and space science. This is where they do much of the analysis. For example, if you remember in medicine, these are the people who will try to understand what is in their drug, what is the structure of the main active compound in a drug. In industries, also there to check the quality of materials that are manufactured in the environment, the amount of, let's say, even pollutants in the environment. In the same with food, what is in the food, it is good for our health. The forensic, these are the people who will look at the we call them the pattern or the fingerprints and anything that deals with crime and anything. Archaeology, archaeology major deals with minerals, so they are the people to determine if what is in the components of things that are majorly associated with archaeology and even space science. So the history of analytical chemistry is that we have what we call classical and instrumental. So before, people just used to do wet method. That is what majorly we call classical. We were just doing what we call separation in classical via what we call precipitation. I think if you remember very well, where maybe you want to separate one particular chemical from another, you might use precipitation method. We were having also extraction and distillation. And then if you qualitative, where we just used what we majorly known as recognition by color, and then even boiling point, solubility, and even taste. You could say that something is acid if it is sour, and something is base by just tasting. Yeah, the taste will tell you what that is. That is that category, we call it classical methods. Then we have quantitative. We know the methods such as gravimetry, and we also have titimetric measurements. These are majorly what is done in our secondary schools, where we do titration and so on and so forth. Then because of some disadvantages with classical methods, these chemists and scientists general worked on modern ways of doing analysis. So you will find, for example, in the case of separation, instead of using things like precipitation, extraction, distillation, we are now using chromatography. If you remember, liquid chromatography, gas chromatography. Then we have another one called electrophoresis, where majorly used in biology. Then in qualitative and quantitative, here we look at interaction between matter and radiation, what we call spectroscopy. So we could look at how their mass are interacting, what we call the spectrometry, like mass spectrometry. We can look at electrical properties or their interaction with the environment, like temperature and humidity. So we are going to dwell mostly in modern instrumental techniques. So for separation, we have the likes of techniques such as gas chromatography, high performance liquid chromatography. We have ion chromatography, supercritical fluid chromatography. We have capillary electrophoresis. We have planar chromatography. And then we have mass spectrometry, and generally here the major difference comes from the ionization source. So based on ionization source, we can have different types of mass spectrometry. That is electron ionization mass spectrometry, chemical ionization mass spectrometry, high resolution mass spectrometry, gas chromatography mass spectrometry, fast atom bombardment mass spectrometry. Then there is liquid chromatography mass spectrometry. We have laser mass spectrometry, ambient ionization mass spectrometry. Very interesting. And so if we still continue with those methods, in spectroscopic techniques, we have a various number of techniques. We have the infrared spectrometry, which we call the IR. There's a Raman spectrometry. Then we have nuclear magnetic resonance, what's called the NMR. Then we have X-ray spectrometry. We have atomic absorption spectrometry. Then we have what we call the ICPS, the inductively coupled plasma atomic emission spectroscopy. Then we have ICP mass spectrometry. We have the atomic fluorescence spectroscopy. Then we have UV-vis spectroscopy, the spectrometry. We have molecular fluorescence, chemiluminescence, and then X-ray fluorescence spectroscopy, or spectrometry, I'm sorry. Then we also have some electrochemical techniques. There's like the voltammetry, the well-known voltammetry. We have potentiometry, we have conductiometry, amperometry. Then microscopic and surface techniques, the likes of X-ray, photon, electron spectroscopy, Auger electron spectroscopy. We have scanning, tunneling microscopy, and atomic force microscopy. So the main thing in analytical chemistry is to solve analytical problem, and the major steps are: you first understand and define the problem by looking at the history of the material to be analyzed and the background of the problem. Then you choose your analytical technique or techniques and running the experiments. Then lastly, you check out data analysis and interpretation. Then you go ahead do what we call validation of results, just in case it is needed, and reporting of results. Those are the three major steps in solving analytical problem. So understanding and defining the problem. So look at what do you want to know and what accuracy is required. Do you just want to know that it is present, or you want to know how much? Is there time that is required? Because different techniques use different. There are fast techniques, slow techniques, and of course some techniques vary in the pricing. So you also need to consider time and money. Also need to know how much sample is available, because different techniques also require different amount of sample. Look at the concentration range of the analyte. You will understand why concentration is a major issue, because of stuffs like what we call limit of detection. Look at what components of the sample may cause an interference. So because some techniques are not very sensitive, and such kind of interferences will not give us good results. What are the physical and chemical properties of the sample matrix? Those are also very important, because different techniques are affected by the physical and chemical properties of the sample matrix. Then how many samples are to be analyzed? Sometimes if there are techniques that can analyze a lot of samples once, but there are techniques you have to analyze each sample one by one, so it takes time. And then history of sample and background of the problem. So background information can originate from many sources, maybe a client and company as product. Let's say you a client can approach you with a problem, or a competitor. Then literature, because most of these things have been worked on before, or related researches. Maybe sample history also can say a lot. How was the sample collected, transported, and stored? Very important. Even the how sampling was done is important. You need to ask. If synthesized by what synthetic route? So that is also very important. The synthetic route that leads to your sample. What was the source of the raw materials used to make the sample? What analysis has already been performed? Those ones you need to ask those questions. So another challenge that many people have is choosing analytical technique. So here you consider the sample characteristics, and then after considering that, choose an instrument, and ultimately a method that can obtain the desired information. Then evaluate the performance characteristics of that instrument and the method. And then if what you have cannot be able to do the work, you can ask yourself, does an entirely new technique need to be developed? So that is your work as an analytical chemist, to know if what you have cannot do the work, so that you start thinking of another technique, a new one. So the technique selection, you look at analysis type. Is it quantitative or qualitative? Look at the location of sample. Is it bulk or surface? So here we mean, for example, like surface techniques are the likes of X-ray. They are what we call surface techniques. And then if we talk of bulk, then we are talking about other techniques such as even mass spectrometry. Then physical state of the sample. Remember, some techniques will require your sample to be in gaseous form, like mass spectrometry. Other techniques will require your sample to be in liquid form, like UVVs. Other techniques will require your sample to be in solid form. Remember, the likes of X-ray. And then amount of sample. Some techniques need a lot of sample. So answer the question, do you need macro amounts? Do you need micro or nano? Because some techniques just need a very small amount of sample. Then fate of the sample. Do you really want to use it after the analysis, or it is something that after the analysis you can just discard? So that will answer the question, do you need a destructive technique or non-destructive technique? Estimated purity of sample. There are samples that you really need to do a lot of purification in the sample preparation stage. So some do not need a lot of purification. So that's why you have to answer that question. You need it pure, simple mixture, or complex mixture. You really need to ask that to yourself, that question. Then analyte concentration. Some techniques just need smaller concentration or lower concentration, but others will need a bit higher concentration. Then elemental information. Do you need total analysis, speciation, isotopic, and mass analysis? Those questions you need to to be about qualitative molecular information. Do you need to know compounds present, polyatomic ionic species, functional groups, structure, molecular weight, physical property? You need to know such. You need to know such because, for example, if you need qualitative molecular information, maybe something like structure. Okay, functional groups, you need something like an IR or a nuclear magnetic resonance. And then and such and such. Molecular weight, those one you need to mass spectrometry. And then components of analytical method. So the method, the first target is to extract data from sample. So that can be done by obtain and store the sample, then pre-treat and prepare sample, and then you go ahead and perform measurements. Then you process the raw data. Then you compare results with standards. Then you convert data into information, and converting data into information involves what we call quantitative and qualitative. So you tell us what amount, and this can be done by applying some statistics, and also interpret data. Is there something or not? Something is missing. Then you transform what you've gotten to information, transform information into knowledge. So this can be done by presentation into graphs, into other ways, graphical methods of data presentation. So how do you analyze data and report results? Analytical data analysis take many forms. You can do the statistics, chemometrics, simulations, empirical interpretations. So analytical result can be reported in peer-reviewed papers. You get a lot from the internet. Technical reports and laboratory notebook records can be subjected to extreme scrutiny and can be challenged by other experts, and that is what we call peer reviewing. After you've done your work, don't hide it. Let people see it. Let them comment. Let them talk about it. Let them correct what they feel was not right. So this is quantitative analysis. There are some terms you need to be aware of, something like precision and accuracy. So if you look at the three diagrams here, the first diagram, this one here, you notice that if this is the center, you realize that these points are very close to each other but very far from the center. So that one we call precise but not accurate. If you look at the second diagram, the points are adjacent to the center but they are scattered. So we call it accurate but not precise because they are not close to each other. Then the last one, they are close to each other and they are also close to the middle, which is the the expected point or amount or whatever. So we call it accurate and precise. So it means that your data should always be accurate and precise. Then what we call selectivity. Selectivity is that the extent to which a technique or method can determine particular analyte under given condition in mixtures of matrices, simple or complex, without interference from other components. So for example, if you have a mixture of A, B, C, and your interest is A, we may say that a technique is selective if it can be able to determine the presence of A in a mixture of A, B, C without A, B, and C interfering. Another word for it is specificity. Then there is what we call sensitivity, is the ability of a technique or method to discriminate between small differences in levels of an analyte. So sensitivity means that if you had a smaller increase in concentration, will give a different response. For example, if you are dealing with a UV vase and you have a calibration curve, a concentration versus absorption, you will realize that a smaller increase in concentration will give a different or a higher absorption. So that means a method is seen as sensitive if it can be able to discriminate between small differences in level of an analyte. Limit of detection. Limit of detection, it is the smallest or the lowest amount of analyte that can be detected at a non-confidence level. So we'll find that most of the methods, if you look at the concentration here, so you'll realize that most methods will have you must have a slightly higher concentration for the detection to be made. Then we have signal to noise. So signal to noise is the ratio of the average signal to the average level of noise. So in most cases, we should not be having too much noise. When we have the noise is higher than the signal, then it means that we are not having a good response, meaning the technique cannot be able to give us good results. The signal should be above the noise. The limit of quantification, it's the range over which quantitative measurement can be made. Limit of quantification, it is the range over which quantitative measurement can be made, usually the linear range. It's where now we start having where the response versus the concentration versus the response start to make a linear curve. That is what we call a linear limit of quantitation. Then we have linearity, the degree to which a response of an analytical detector to analyte concentration approximates a linear function. So we expect that if you add a small amount of a unknown, then we expect that detector response is also improving linearly. So adding concentration means also higher detector response in a linear way. Then dynamic range between the limit of quantitation and limit of linearity. It means we have limit of linearity, a point where even if you add concentration, the detector response now misbehaving. It is not increasing in relation to the concentration. So at the point where we have what we call the limit of linearity, and a point where now we can start having what we call the range over which quantitative measurement can be made, that is what we call dynamic range, and you can be able to see it here. Then all that can be done using calibration curves, and a calibration curve is a measure of signal response versus non-analyte concentration. So you cannot do calibration curve without a non-analyte concentration. So you do, data is plotted and fed to a function to obtain an equation of the best fit and a certainty in the fit. You know the equation is always y is equal to mx plus b, where y is the y-axis response, and x, which is unknown, or the known, is the concentration, and m is related to the method sensitivity. We remember very well that when you say the word sensitivity, it means where a method can be able to discriminate in the small difference, in the concentration of the analyte. So it means that if our method is very sensitive, then our m will be small. So then we do measure the sample response to determine the concentration. So that is now when we have our unknown. After we do the calibration curve, if you want to know the concentration, we put some amount, and then we get the response, and then from the response we can use our calibration curve to get the concentration. We try as much as possible not to have a pure, to have a sample that is not having a lot of matrix, because matrices also have interferences. So there are different types of curves, but this is what we call linear least square or linear regression, where we can always use this to in our calibration curves to calculate the linear regression. You can see how we are doing it, because at some point you will find that if you check this, you realize that you realize here that the point here is very close to the linear curve. This one is very far. Now what we call linear least squares is now the mean of all those points from the linear the linear curve, or the residuals, or the line of best fit. So this is how generally it is done by hand, but you don't have to do this by hand. We always have softwares or programs like Excel, MATLAB to do that. Then correlation coefficient can also be calculated, a fraction between 0 to 1. So if we have our correlation tending towards 0, then it means that the comparison between our data and the linear curve is very low. We say when we are tending to 1, then it means that our correlation is high. So correlation is dimensionless, it has no units. It's just the sum of residuals associated with the linear relationship. And then so if R square, which is the regression or correlation coefficient, is near to 1, the regression model fits the data much better than the null hypothesis. We know that the null hypothesis says that there's no correlation. So if there is correlation, it means that R square is tending much to 1.0, then we say that there is correlation actually. If the regression model were not much better than the null hypothesis, R square would be near 0. So if you are using calibration curve, that is what we would expect. And we see how we can work out that. Peak area of 2.65. So 2.65 will be somewhere here. And then we work it. We draw a straight curve from y-axis to our regression curve or line, and then we draw down to the concentration, and we come up with 1.14 mole. There are different types of curves. So we have even what we call the standard addition method. We won't talk so much about it now. Just know that you take the known quantities of analyte are added to a sample of a known concentration. So here, this is good for system with significant matrix effect or the interferences where selectivity or specificity is lacking. So that's why we do standard addition method. And then so you can see the example. If you have atomic absorbance measurement of zinc, for that, you can see the intercepts there. You can see the equation y is equal to mx plus b. So you can see that the slope there for concentration, the slope there, which is m, is 0.179. Then the intercept is 0.199. So you can be able to see that we can now be able to work for x, which is the concentration. So if the absorbance at that point is 0, then we can be able to work out that the zinc in the sample is 1.11 parts per million. So that is it. That is it. Because you can be able to see that when the concentration was 0, already the absorbance was 0.2. Nonlinear fitting, we have other calibration curves. For example, there are the logarithmic functions, the likes of the Nast equation. We done it a lot, you know it. We have the exponential equation, like the Halley's model for immunoassay. We have the Colroth's law. If you guys remember the conductivity of dilute solution in the, then we have the polynomial, that immunometric assays. So much of the reading we can do is the Scooge et al. That book, Analytical Chemistry by Scooge. Thank you. Subscribe and like my channel.